Okay, so now we're on to the remainder theorem. Now remember that the factor theorem told us that if the remainder was 0, then it told us what a factor was. This is kind of a converse because it tells us if we divide a polynomial by this term, a linear factor, it tells us what the remainder is going to be. So if we divide by ax minus b, the remainder is going to be what the number is when we evaluate the polynomial at b divided by a. Now we're going to do an example and we're going to kind of see where this number comes from. So we're looking at this polynomial. It's a quartic. We have a polynomial of order 4. And we want to know what the remainder is when we divide it by this polynomial. So let's, first off, let's use the theorem and see what we get. And then we're going to do polynomial division to kind of see why that might be true. So just linking this with the theorem, we have the a term equals 2 and the b term equals minus 1 because we have a minus here. So we need to find b divided by a, which is actually going to be minus a half. So we want to evaluate f at minus a half. And by this theorem, whatever number we get is going to be the remainder. So let's just put minus a half into here. We have 8 times minus a half to the power of 4, minus 4 times minus a half to the power of 3, plus 12 times minus a half squared, and minus 1. So you can either use a calculator or we're going to do it by hand now. We have 8 times this to the power of 4 comes out as, so half, a quarter, an eighth, 1 over 16. And the minus disappears because this is an even power. And then this is, so we have minus 4 times, so minus a half cubed is minus 1 over 8. And I'm going to bring the minus with this, going to combine it with this one, and this is going to turn it into a plus. This is fairly simple algebra, so we have 12, this is times a quarter, we have minus 1 here. So let's just simplify everything. We have 8 over 16, that's a half, 4 over 8, that's also a half. This 12 over 4 is 3, and we have a minus 1. So this turns to 1, this is a minus 1, so we're left with 3. And so what this theorem is telling us is if we divide this polynomial by this linear term using long division, polynomial division, we should expect to get a remainder of 3. And now we're going to do that now just to confirm it, and we're also going to get some insight into why this is true. So let me just rub off the board to clear up some more space. Okay, so I've just rewritten out what we want to do. We want to divide this polynomial by this linear factor. So we use polynomial division, which is something I've already covered in another video. So let's go through it fairly quickly. We take the leading term here, so we look at 8x to the 4, we divide it by this term, and this gives us 4x cubed. Then we take this and we multiply it by this factor. So we have 8x to the 4 plus 4x cubed, and we subtract this off from our first line, our polynomial up here. And if we do that, these cancel, the first term cancels, and we get minus 8 cubed plus 12x squared minus 1. And then we repeat, so we look at this leading term and we divide it by 2x, and this gives us 4x squared. And then we multiply down, and then what we're left with, so 8x cubed minus 4x squared. And then write brackets and subtract this term off the previous line. So the first term is going to cancel again. And then now we have the minus, double minus, which is going to turn to a plus. This gives us 16x squared minus 1. So let's do it one more time, or maybe 2 more times actually. So divide 16x squared by 2x. This gives us 8x. Then bring it down and multiply, and this gives us 6x squared plus 8x. And then if I subtract this term off, we actually have an x term here, and we don't have one up here. So we're actually going to get minus 8x minus 1. So we have to do this one more time to get rid of the x's. Divide minus 8x by 2x, and we have minus 4. Then one more step, we just multiply this down, and we have minus 8x minus 4. Subtract this factor off, and what are we going to get? So we can have minus 4, which is plus 4, and we have minus 1, so we have a remainder of 3, which is exactly what we expected from our previous workings out. Remember that we evaluated this polynomial at minus a half, and it told us the remainder was 3. So this is to confirm that this theorem is doing what we expect it to do. So as a last remark, let's just think about what this is actually telling us. So we know that when we divide this quartic by this linear factor, we get this whole remainder, this whole polynomial, and we get a remainder of 3. So we can actually write this out algebraically. So we have 8x to the power 4 minus 4x cubed plus 12x squared minus 1. And from this calculation, it tells us that we can factorize this as 2x plus 1 times this, our answer, this cubic, which is quite long, so 4x cubed minus 4x squared plus 8x minus 4. And we have a remainder of 3. So this is just comes out here, so we have plus 3. So this is exactly what our calculations tell us. And now we can think about why this theorem might be true. Because we factorize this polynomial, I wrote it as f of x. This is what we called it. We factorize f of x, so we kind of divided it by this term, and we got this other polynomial. But we also got this remainder. So now think about, if we evaluate this polynomial at the number that makes this bracket equal to 0, then this whole term is going to vanish, because we're going to have 0 times another number, which is just 0. And we're going to be left with exactly the remainder here. So now we need to think about, when is this bracket equal to 0? And it's exactly when x equals minus a half. So this is why when we evaluated this at minus a half, this turned to 0, this cancelled, and we just got the remainder 3. And this is where this theorem comes from in general. So if we can see that if we evaluate this term at b over a, then this linear factor equals 0, because a times b over a minus b, well, the a's just cancel and we get b minus b, and this equals 0. So this is where this number comes from. It's exactly when this bracket equals to 0.